Let's go ahead and start chapter 14. But before we start chapter 14, let's review what we did in the first half of this course. We started in chapter 1 and we basically learned some review of things that we had already seen in general chemistry. The same thing for chapter 2. We learned a little bit about acid-base chemistry. We learned about making structures. We learned about all kinds of other things. Then in chapter 3, we learned to name alkanes. In chapter 4, we learned about the alkyl halides and free radical reactions. Then in chapter 5, we learned about chirality. In chapter 6, we learned about SN1, SN2, E1, and E2 reactions in chapter 6 and 7. And then in chapter 8 and 9, we started learning about the different functional groups. And we learned about alkenes in chapter 8. We learned about alkynes in chapter 9. Then in chapter 10 and 11, we learned about the reactions of alcohols and then the reactions to produce alcohols. So we learned all kinds of chemistry of alcohol. So we've covered basically 3 functional groups: alkenes, alkynes, and alcohols. What we're going to do in this semester is we're just going to go through the other functional groups. So in chapter 14, we start with ethers. So let's just talk about what an ether is. An ether is a compound that contains a carbon-oxygen-carbon bond, where both of these carbons do not have oxygens attached to them. Other oxygens like C double bond O's or anything like that. So this is an ether. Now, just as we've classified compounds, what we're going to do in this chapter also is classify the compounds by the type of ethers. There is something called symmetrical ethers and unsymmetrical ethers. And then there are what's called cyclic ethers. A symmetrical ether would be an ether where the 2 R groups that are attached to the ether are the same. For example, this one has 2 ethyl groups on it. This would be an unsymmetrical ether. Notice on one side we have a methyl group, and on the other side we have an ethyl group. So these are unsymmetrical ethers. Now a cyclic ether, listen carefully, has the oxygen as part of the ring. This is a cyclic ether. This is not a cyclic ether. Notice the oxygen is there, there's a ring there, but the oxygen is not part of the ring. And being able to identify ethers as cyclic ethers, symmetrical or unsymmetrical, is going to help us as we learn to name them and learn the few reactions that ethers undergo. Ethers are compounds like alcohols. If we were to draw the structure for methanol, we could draw this structure with the 2 lone pairs on the oxygen. Notice that this ether looks very similar. So ethers are polar just like alcohols. But what's the big difference? Can ethers hydrogen bond with themselves? No. But can they hydrogen bond with water? And the answer is yes. So on the test, I could ask you to show how an ether will hydrogen bond with water. Although it has no hydrogen attached to the oxygen, notice it can still hydrogen bond. The hydrogen on the water can bond with the ether, the oxygen on the ether. This makes ether slightly soluble in water, okay, but not very soluble. Notice the alcohol can hydrogen bond the same way, but it can also hydrogen bond with the hydrogen on the alcohol with the oxygen on the water. So notice alcohols can hydrogen bond much more effectively. Okay, so this is it can hydrogen bond with water, but it can't hydrogen bond with itself. Since it can't hydrogen bond with itself, then ethers have much lower boiling points than do alcohols. Okay, so if I gave you a question on the test and asked you which one of these 2 compounds has the higher boiling point, I would expect you to be able to answer that question based upon what you saw or which one is capable of hydrogen bonding, okay? Now, let's go over to page 2. Now, this is going to bring up something very, very important. Not so important in chemistry as it is in medicinal fields, and we've already talked about this before. If we think about ions in solution, let's talk about lithium ions. Lithium ions, whenever you put them in water, the water molecules encircle the lithium ions, and that's how it keeps it in solution. Well, the same thing can be true if these are ethers. Ethers will solubilize ions, okay? They will solubilize ions. So certain ions will be soluble in ether solution because this same type of thing occurs. Notice it's the oxygen end that points toward the lithium because the oxygen is the one that's donating the electron pairs. The oxygen is partially positive. Now this brings us to crown ethers. And notice in your notes, if you're following along on your notes, we've got 2 ethers there, and these are crown ethers. We've talked a little bit about crown ethers in a previous lecture, but we want to talk about them in a little bit more detail. If I have a lithium ion, it can be solubilized by something called 12 crown 4 ether. Now, a crown ether is nothing but a ring of compounds or a ring of atoms where we have oxygen, carbon, carbon, oxygen, carbon, carbon, oxygen. Notice if you count the number of things in this ring, it's 12. There's 4 oxygens, so this is called 12 crown 4 ether. Now that forms a cage, and that cage is perfect to catch a lithium ion. But if you look at a sodium ion, looking at the periodic table, sodium is 1 period lower than lithium. It takes a bigger crown ether to catch it. So the crown ether that forms the correct size cage for sodium would be 15 crown 5 ether. Now let's go back to general chemistry. If I asked you, is sodium chloride soluble or not? What would you say in water? Yes. Why? All group 1A salts are soluble. You probably learned that somewhere down the line. So would lithium chloride also be soluble in water? Yes. So could I use water to separate lithium ions from sodium ions? And the answer is no, because both of them are soluble in water. But I could add 4 crown 12 or 12 crown 4 ether. It would solubilize the lithium ions. The lithium ions would go up into the ether layer. The sodium ions, since they don't fit in this cage, would stay in the aqueous layer. So we can separate ions using the extraction method that we learned last semester by putting a crown ether in with their water mixture, shaking it. The lithium would go up into the crown ether and the sodium would stay in the water layer. Now this same thing is used again, like we talked about last semester, in something called chelation therapy. Chelation therapy, they don't necessarily use crown ethers, but they use these cage molecules that will wrap around metal ions. So if you get metal poisoning, like mercury poisoning or lead poisoning, they use special caged molecules called chelating agents. And what they do is they do the same thing. They extract the metals up into them, and you can easily remove them from the body. Now, 2 other compounds that we're going to talk about. And we're going to talk about this for just a few minutes. Now listen carefully for those of y'all who are going into a health field. This is the type of question that if you understand what's going on here, it's going to help you whenever you get into studying the interactions of molecules in the body, drug interactions and everything. And you're not expected to get this answer right at this moment in time. But by the time we finish this discussion, what I hope you get out of this, and this is not really something that can be easily tested, but it shows whether you understand the concepts or not. And in organic chemistry, I know what y'all are saying, it's all just a bunch of reactions and stuff, but the concepts are the part that I want you to take out of this course so that you can later on apply these to any situation you get in pharmacy school, med school, PA school, all of those types of health fields that you may go into. Now, there's two different reactions here. And let me see, I need to go up high on the board here. So let me just move that back a little bit. The first reaction is B2H6 plus 2THS yields 2 BH3.THF. Now that reaction doesn't mean anything to you, okay? But I'm going to show you what the structure for B2H6 is. Now somebody tell me what's wrong with that Lewis structure. What's wrong with that Lewis structure?
Hydrogens have two bonds on them.
And hydrogen's not allowed to have two bonds, except it is. But this is not really the correct Lewis structure. The way we can draw this is we can draw an arrow there and an arrow here, okay? Saying that because boron doesn't have enough electrons around it without that arrow, without that hydrogen, the hydrogen is forming a partial bond with it. It's sort of like a hydrogen bond. It's not a true bond, but we oftentimes write it as a true bond, okay? This is called a dative bond, a dative bond. Now, what happens with the THF? This is the structure of THF. It's a cyclic ether. Okay, it's a 5-membered ring with an oxygen here. And remember, this oxygen has lone pairs on here. And what these oxygens do is they come in and replace that dative bond. Okay, so here's what the structure looks like whenever we get finished. The boron has 3 hydrogens around it, but then the oxygen comes in here. Now remember, the oxygen's on a cyclic ether, and one pair of the electrons gets shared with the boron. If we were to calculate formal charges here, the boron would be negative and the oxygen would be positive. So what happens is this THF molecule donates its electrons, okay? Now, the second reaction we have here is that BF3 reacts with diethyl ether. And it does the same thing. The boron, having 3 fluorines on it, hooks to the ether, and does the same thing. The boron is negative and the oxygen is positive. Now, here's where the thought process comes in. And I want you to, this is not in the notes, so I want you to just think about this for just a minute. Now listen carefully. Whenever you react the B2H6, THF will react with it. Diethyl ether will not. So this ether is a good enough ether to form this complex. This ether is not. Okay? Both of these will form a complex with BF3. I'm just showing this one. Now listen to the question, and I want you to actually listen and see if you can formulate an answer. And let's pretend that you were sitting in your pharmacy school class, your medical technology class, your medical school class, and they asked this question, and you're wanting to impress your instructor because he's going to be the one who's going to assign your rotations in the next part of your career. First of all, BF3 will react with both compounds. B2H6 will only react with this one. What does that tell me about the reactivity? Who's more reactive, B2H6 or BF3? Since BF3 will react with both of them. The BF3 is more reactive. Now, somebody unmute your mic. Daniel, you've already answered, so you hold off on this question. And tell me why BF3 is more reactive. Kylie, why is BF3 more reactive? If I wanted to draw the structure for BF3, it would look like this.
Would it have to do with the dative bonds?
Okay. Now, in this case, we've got dative bonds. We don't have dative bonds here. So one of the things, the reason the BF3 is reactive is exactly the dative bonds. For an ether to come in, it's got to break the dative bond here. There is no dative bond here. Okay. So the dative bond, the lack of a dative bond makes this more reactive. Now, remember what's happening. This pair of electrons is coming in to form a bond with the boron in both cases. Now, let me ask a question. Why is this boron more susceptible to attack than this boron? Somebody else. Taylor Hawk? Why is the BF3 boron more susceptible to attack than the boron up here? What else is different? Riley, what do you think? What's the obvious difference?
I mean, the obvious difference is the dative bond.
Okay, and what else? What atoms are attached to the boron here?
Oh, hydrogens,
And here?
fluorine.
And what do you know about fluorine?
It's electronegative.
Which means it does what? Pulls electron density in that direction. Now, since you're pulling electron density away from the boron, would that make it more susceptible or less susceptible for other electrons to come in? It's going to be electron deficient. So therefore, what's going to happen? It's going to want electrons more. So those two reasons explain why BF3 is more reactive than the B2H6. The lack of a dative bond and the fact that it's got electronegative atoms on it. Now that is actually the easier of the two questions. Now the other question. Notice that this ether will react with both compounds, but this ether will only react with the more reactive boron compound. So this ether is much more reactive than this ether. Now tell me why. What's not different about them this time? There are no fluorines, so that's not the answer. So what is the answer? And this is the part that I want you to pay particularly close attention to, because this is the part that's really comes up over and over and over again in biological chemistry. Why is this ether much more reactive than this ether? Summer, how many carbon atoms are on the bottom ether?
4.
How many total? 4. How many on the top ether? 4. What's the hybridization of all the carbons? sp3 in every case. So what's different about them? Now, hopefully you'll be able to see this on the models, but this is the cyclic ether, okay? Notice I'm letting the blue atom be the oxygen and these be the lone pairs. Notice this is the non-cyclic ether, okay? We've got the two ethyl groups. Do they look much different whenever I hold them like this? Not at all. Both electron pairs are equally available. But remember, on the non-cyclic ether, there's free rotation here. So watch what I can do. I can rotate this molecule into this conformation. Now pay attention here. If you look at this, notice this conformation. Can I rotate this molecule up here? No, because they're held together here. So notice these electron pairs on this one are much more exposed. I can't ever block, no matter what conformation I put this in, I can't block these lone pairs. But notice in this one, these methyl groups can come across and block those lone pairs. Okay, I can pull these across and block the lone pairs. Whenever you're looking at reaction rates, okay, in organic chemistry, if the reaction occurs via the the donation of a lone pair, anything that makes those lone pairs more susceptible to be able to be donated increases the rate of reaction. Anything that blocks those lone pairs lowers the rate of reaction. So for those of y'all who are going to pharmacy school, you're in a medicinal chemistry class. They're talking about this drug interacts with the body much, much slower than this drug. What's the reason? Well, if there's electronegativity involved, that's probably something you need to look at. But notice in this one and this one, there's really no difference until you think about the fact that these electrons cannot be blocked by the rest of the molecule. So these electrons are easily able to be donated, whereas these electrons can go into a conformation in which the electrons are blocked and therefore can't be donated. And that comes up over and over and over again in biological chemistry. So keep that in mind. And it's hard to give a test question on that. But again, it's going to come up in so many concepts that we're going to cover throughout this course. You know, those kind of, not necessarily that thing, but these types of concepts. And one of the things that organic chemistry is supposed to teach you is how to think differently. And hopefully that's what you're able to do. You're able to see how these concepts are going to apply in other situations. So now, that gets us over to where we're going to actually have test questions. And the first thing that, like we do with any other functional group, is we learn how to name compounds. And we're going to learn how to name ethers, and we're going to learn two different ways to name them. And you're going to have to know both of them, the common way and the IUPAC way. The common way to name ethers is to look at the oxygen and name the two groups that are on both sides of it. Okay, so if I look at this, attached to the ether oxygen, notice I have an ethyl group and a methyl group. So we would just simply name this compound ethyl, methyl, ether. Okay, that's all there is to it. How would we name this one if the two groups are the same on both sides? We call it diethyl ether. Okay, we just put them in alphabetical order if they're different, and we say di if they're the same. So if we have a symmetrical ether, we would just call that diethyl ether. Okay. Now, look at this one. Those are cyclohexyl rings, cyclohexane rings. So this would be dicyclohexyl ether. Now, if I put double bonds in there, What are those groups called? Does anybody remember?
Benzyl groups.
Not a benzyl, because it's just the ring itself. The benzyl would have a CH2 hooked to it. It's the other one. Starts with a PH. The phenyl group. So this would be diphenyl ether. Okay, does everybody see that? Okay, so don't mix up the cyclohexyl groups and the phenyl groups. Now, that's all there is to common names. But obviously that gets very complicated if the groups that are attached are not easy to name. So we have a IUPAC method of doing this. Now I want to name this compound here. But before I name that one, I want to name this compound here. Do you agree that you would name this as an ethane? And you would name this as the substituent. And you would say chloroethane. Now, we're going to do this a lot when we name compounds. When we're trying to figure out how to name it, we're going to compare it to naming the chloro. Because if you can name the chloro, then you can name any other type of compound. So what's different about this one? We still have this and this substituent. So it's still going to be an ethane, but what do we call that substituent? Now, whenever we have a substituent that has an oxygen and then an R group attached to it, we name this as an alkoxy group. So this is methoxy. So this group is called the methoxy group because it's a methyl attached to an oxygen. So what would this compound be called? Methoxy ethane. One word, no spaces. Notice we don't need a number in this case to tell where the methoxy is attached. Okay, that's all there is to it. So this is just a substituent. Notice we took our longest chain to be our main group. So let's look at a couple of more to just bring in some concepts from previous chapters. If I have this, and notice I'm going to draw it this way. I drew it the other way in my notes, but on the board I'm going to draw it this way just to show you that you can have both ways. Now, when you draw this group, make sure you show that the oxygen is the part that's attached to the ring. Don't write it OCH3, okay? Now, just as I showed in my notes that it was trans, notice I'm showing here that they're trans. So here's my main thing. Notice it's a cyclohexane. And then I just named this piece and this piece as substituents. This is called methyl. What's this one called? The methoxy. And again, we put them in alphabetical order. Now, in this case, do you agree no matter how I number it, I'm going to have 1, 2, 3, 4, or 1, 2, 3, 4. So in this case, how do I know which one gets the 1 and which one gets the 4? We've done this before with all of our other compounds. Since the numbers are exactly the same, then what do I do? The one that's first in the alphabet is the one that's first gets the lower number. And who's first in the alphabet? Methoxy comes before methyl. So this would be 1 methoxy, 4 methyl cyclohexane. Again, no spaces. And again, if you have trouble with that, put a chloro on there and see how you would name it. Okay? And then you're going to use exactly the same rules. Now, again, don't look at the next one on the notes, but let's see how you would name the next one. Now, notice this is called the ethoxy group. It's an ethyl group attached to the oxygen. And over here we have methyl groups. Now this one's first in the alphabet, but do I number 1, 2, 3, 4, or do I number 1, 2, 3, 4? Which is correct here and why? Who wants to take a shot at that? Which one is correct and why? Do I use the numbers inside the ring or outside the ring? Which way? I use the numbers outside the rings because notice that gives me 1, 1, 4, and the numbers inside would give me 1, 4, 4. So the numbers are not the same in this case. Okay, so this would be 1, 1. Okay, it would be 4 ethoxy because we still put them in alphabetical order. 1, 1 dimethyl. Remember, we use prefixes when we have more than one. Cyclohexane. Okay. And I guess I used 3-methoxy in my notes. I put 4-methoxy here on the board. Okay. Any question on that? Now, those are the easier ones to name. What we're going to do now is we're going to learn to name cyclic ethers. Now, what I suggest you do with pages 4, 5, and 6, which is naming the cyclic ethers, okay, is make you a nice piece on your next note card and everything with these rules on how to name these. Now, the cyclic ethers that we're going to learn how to name are the ones that are more common. These are the 3, 4, 5, and 6-membered cyclic ethers. And the 3 members are the hardest, okay? Because the 3 members have 2 common name methods for doing it, and then 1 systematic name for it. Now, the 3-membered rings, and I'm going to try to keep all of this on the board at the same time. The 3-membered rings are called oxyrings. Now, the common name for these are called epoxides. So there's 3 different ways to name this. Now, the first way to name it is this. If we have this compound, notice the 3-membered ring will always be attached to the whatever it's attached to. Okay, so here's my 3-membered ring. Now, this 3-membered ring piece is called oxide. But what you have to do to name the compound using this first method is you have to realize that this compound came from reacting cyclohexene with the peroxy acid. Now pay attention here. So the peroxy acid, and I think the solvent was CCl4. If you look back in your Chapter 8 reactions, you have that reaction. The way you name these compounds using the oxide method is you name the alkene from which it was made and then change the alkene to oxide. So this would be cyclohexene from which it was made and then oxide. So to use this method, we must be able to know what alkene it came from. So you have to understand the Chapter 8 reaction. Now, if we have this oxide, notice that the 2 methyl groups are cis on the ring. This came from this alkene. Since the methyls are cis on the ring, the methyls had to be cis in the compound. So this is what? What's the name of this compound? But-2-ene, because notice the double bond is between the third and fourth carbon, and it was cis but-2-ene. So this would be cis but-2-ene oxide. Okay, I think in the notes I left out the 2 part in there, but you do need the number 2 in your answer. You don't need a number in the ring because it's understood to be there. So this is the method that you use for the 3-membered rings. Okay, now the second method here is to, let's again look at this compound, and we're going to name this whole piece as a functional group. And the way we name it as a functional group is we're going to name it as an epoxy group. So we're going to number our carbons just like we would always do. 1, 2, 3, 4, 5, 6. And we would call this cyclohexane, but we would name this whole piece as a functional group. So this would be 1, 2, epoxy. Notice we put the numbers 1 and 2 in there, epoxy with a Y, because it's a ring between the number 1 and 2 carbons. And then we just named that as a functional group, cyclohexane. Okay, so that's all there is to that. So if we wanted to name this same compound over here, doing the same thing, how would we name it? Again, this is butane, okay? So this is my epoxy group. So again, it's going to be 2, 3 epoxy. Does everybody see why it's 2, 3? Because it's between it's the 3-membered ring hooked on the number 2 and number 3 carbons. Butane. Okay. And again, it's cis because these 2 methyl groups are cis on the ring. Not because of a double bond, but because of their position on this ring. Okay, that's all there is to this. The third method is the systematic method. And we're going to look at the systematic method because all of the rest of the compounds are only going to be named by the systematic method. The systematic method says this compound by itself with no hydrogens on it is called oxirane. O-X-I-R-A-N-E, oxirane. Now, if we have 2 methyls on here, okay, when we name it as an oxirane, we always number letting the oxygen be the number 1 carbon. So the systematic method of naming all of these different cyclic ethers always lets the oxygen be the number 1. Notice in this case, it doesn't matter which way we number it. So we would name this 2, 3 dimethyl, because what are the groups that are attached to the oxirane itself? A methyl and a methyl. And again, since they're cis on the ring, this cis and trans shows their position on the 3-membered ring. So, which method do you like better? I don't like this method at all because it requires us to have to go back to the alkene that it was made from. This one kind of halfway makes sense, but this is the much more systematic. Now, you need to know all 3 of them. If I asked you to name a compound that's a 3-membered ring on the test, you can name any one of them. You can name it any of the three ways. But if I give you the name, I could give you the name in any of the three ways. So, you need to know how to name three-membered rings by all three of these methods. Naming it as an oxide, naming it as an epoxy, and naming it as an oxirane. Now that brings us to all the other groups. And there is no trivial names for them. They're all named as the systematic way, pretty much. So we said the three-membered ring was called oxirane. Now, having known how to name it, don't look down in the notes yet. The four-membered ring is called oxetane. And again, you get to put these on a note card so you don't necessarily have to memorize these. O-X-E-T-A-N-E, oxetane. So knowing that is oxetane, using the systematic way of naming this, name that compound. Okay, the last thing we're going to write is oxetane. What's attached to it? Where do I start numbering? I start numbering at the oxygen. In this case, it does matter which direction I number from, don't it? I'm going to number 1, 2, 3, 4 to keep the numbers as small as possible, just like we've always done. So this is going to be 2-ethyl, 3,3-dimethyl oxetane. Okay. Again, if we had cis and trans on the ring, we could show that. Notice I'm not showing stereochemistry here. Okay, so that's all there is to that. So the four-membered rings are called oxetanes. Now listen carefully. I want to do this a little bit differently on the board than is in my notes. The five-membered ring with an oxygen in the ring is called oxolane. Now, once you get above the four-membered rings, we can have things in here that have double bonds. So we could replace and put one double bond in there. We could also put two double bonds in there. Now this compound has a special name. It's called furan. Now pay attention to what we're going to do when we go from furan to this compound to this compound. Notice what happens. We lose a double bond, and it doesn't matter which double bond we lose. So when we lose a double bond, really what we're doing is, I'm going to put some hydrogens on here, just on this side of it though. And notice what we've done. To go from here to here, what have I done? I've added two hydrogens. So this compound is called dihydrofuran because we have taken furan and adding two hydrogens to it. What would this one be called other than oxalane? To go from here to here, haven't I added two hydrogens on either side? So I've added a total of 4 hydrogens. So this compound is often called tetrahydrofuran. And it's abbreviated THF. Remember, we talked about that compound earlier whenever we were talking about the exposed electrons. So this is furan, dihydrofuran. or tetrahydrofuran. And tetrahydrofuran is also called oxalane. Okay, so now, having said all that, I want you to name this compound. And I'm even going to show the stereochemistry here. So this one's not in your notes, but can you name that compound? That would be a good test question. Now you can name it two different ways. You can name it as an oxalane, or you can name it as a tetrahydrofuran. I'm going to name it as an oxalane. So if I name it as an oxalane, where do I number from? I number from this oxygen, 1. Now, it doesn't matter which way I number in this case. Do I number clockwise or counterclockwise? Which is correct in this case? And again, this is where most students lose the points on the naming part of the test. And there's going to be less partial credit this semester because I expect y'all to be a little bit better at it. So do I number clockwise or counterclockwise? If I number counterclockwise, this is going to be 2, 3, 4, 5. If I number this way, are the numbers inside the ring or outside the ring better? Inside the ring, notice puts my substituents at 2 and 4. Outside the ring puts my substituents at 3 and 5. So notice inside is better, even though that doesn't give chlorine the lower number. So what do I say? I would say, again, whenever I write them, though, I do write them alphabetically. It's 3-chloro, 2-methyl, oxalane. And again, I've shown these groups as if they were trans, so I need to put the trans out here. Okay, any questions on how to name these? Now let's look at the last one. So we've got the oxalane, we've got the oxetane, and we've got the oxirane. Now let's look at the 6-membered ring. The 6-membered ring, I'll go ahead and put the oxygen at the bottom just so that I can be consistent with the previous one. A 6-membered ring is called the oxane. Okay. Now, just like the oxalane, it can also have double bonds in it. It can have 1 double bond or 2 double bonds. And notice both double bonds are in conjugation with the oxygen. Notice what I mean by conjugation: double bond, single bond, and then the oxygen. Okay, so if we have the 6-membered ring with 2 double bonds in it, it's called pyran. So the common name for this is pyran. So again, we've added 2 hydrogens. So notice this is dihydropyran. Notice we've added 4 hydrogens to the top one. So this is tetrahydropyran. So notice we've got pyran, dihydropyran, and tetrahydropyran, but it's the same thing as oxane. Now, to make this more complicated, whenever you get to the and if you're looking on my notes, let me clarify this before we go any further. I've got this structure here, and I've got that labeled as 3-methylpyran, I left out my double bonds. Okay, so make sure you put the double bonds in there, okay, for that structure. Notice the way I have it drawn on the notes would be 3-methyl tetrahydropyran. So either, change the name or change the structure. Now, I want to do one last thing with these pyrans. To make things more challenging than that, the pyrans exist where you can also have 2 oxygens in the ring. And they come in 2 varieties. This is called 1,4-dioxane, okay, because notice it's an oxane, but there's 2 of them. So this is 1,4-dioxane. And what do you think this one would be then? 1, 2, 3, 1,3-dioxane. Now, if you have your cell phones handy, go ahead and get your cell phone out and get ready to do a search in just a second. Okay? This compound is called oxane. These compounds are called dioxane. Dioxane is oftentimes used as a solvent. It is spelled D-I-O-X-A-N-E. Pronounce that to yourself. Say it out loud. You don't have to open your mic. Just say it out loud where you are. Dioxane. Now, I want you to pronounce this word, D-I-O-X-I-N. Dioxane. 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 They sound a lot alike. I want you to do a Google search on dioxane. Okay, search dioxane, Ukraine, poison. And don't go to images yet. Type in dioxane, Ukraine, poison. Whenever you find an article, whoever finds the article first, just buzz in and read some of the highlights of that article. One of y'all who can read, okay? And share with the class so everybody can hear you. So somebody just jump in. Go ahead, Sarah Edwards. I know you can read. Did you find anything? Kylie, did you find anything?
Yeah, I saw that there were some presidential candidates that felt ill and had face disfigurations and blotches.
Okay. So this, we think politics is bad in the United States. This Ukrainian presidential candidate was poisoned with dioxin. And you said some of the symptoms were face disfiguration and everything. Now go to the images and look at a before image and an after image. It's a pretty disturbing image. They poisoned this guy with dioxin, and look at the disfiguration it had in it and everything. Dioxin is a poison, and unfortunately, it's a byproduct of some chemical reactions, and it's toxic in the parts per billion range. Okay, so let's suppose, Daniel, you decide you want to do what? You want to go to, med school is not for you. You want to be an environmental chemist. You want to save the planet. Okay, and you go out and take water samples, and you find water samples in the parts per billion. That means 1 gram. Let's look at what a parts per billion means. And dioxin is toxic in those levels. What does a parts per billion mean? 1 part per billion. So that's 1 gram of dioxin per 1 billion. That's a whole bunch of zeros. Grams of a substance. Now watch this. 1 part per billion. 1 gram per a billion grams. That's a, let's just take away 3 zeros. That still leaves us 9 of them. Or is that billion? That's billion there. Okay. Whoops, I had too many zeros. Sorry. That's a billion. Okay. So 1 gram per 1 billion grams. That's 1 gram per 1 million kilograms. We all know what a kilogram is. That's 2.2 pounds. That's 1,000 metric tons. So if you took something that was toxic at the 1 part per billion range and you dissolved 1 gram in 1,000 tons of dirt, 1 gram, and we all have went to the lab and weighed out something that's 1 gram, and dissolved that, spilled it in 1,000 tons of dirt. Now, if you want to think about what that means, that's about 12 dump truck loads of dirt. Okay, 1 gram in 12 dump truck loads. And it makes the ground unusable and everything. Whenever you're talking about parts per billion, it's a really, really small number. And of course, if you read this story, it's got a lot of intrigue to it and everything. How this all came about happening, who they actually found out that was responsible for the poisoning and everything. And if you like air politics and think air politics are crazy, go over to this story and you'll find out that ours is not as crazy as some of the other countries. Okay, so one of the things we want to talk about with ethers is the reactions of ethers. And luckily for ethers, there's not going to be many reactions. Okay, so the first test this semester won't have a lot of reactions on it. The first reaction we're going to discuss is one we've already discussed, the Williamson ether synthesis. Remember, we said that you could take an alcohol and react it with sodium metal or sodium hydride. We used both of these last semester. And what that basically did was deprotonate the alcohol. Okay? Now, we could finish the reaction, but all we really cared about was that it deprotonated the alcohol. This then could act as a nucleophile. So we took this and reacted it with an alkyl halide. These two R groups don't have to be the same. This comes in, backside attacks, breaking this bond, kicking the halide out, and we get an ether. We talked about this reaction last semester. Now, notice that the second step of this reaction is an SN2 reaction, which means this alkyl halide that we use needs to either be primary or secondary. And it can't be sp2 hybridized carbon that the halogen is attached to. So here's a question on the test. I want you to design a Williamson ether synthesis to make this alcohol. That's all it's asking. Make this alcohol using the Williamson ether synthesis. Now, there are 2 different ways to do this. I could start with this alcohol, reacting it with sodium metal. I'll choose sodium metal instead of the sodium hydride. What does that do for me? Deprotonates the alcohol. Then what would I react it with to put the CH3 on there? CH3, and I'm going to put the chlorine on this side. Notice this would come in, backside attack, kicking off the chlorine. Would that give me the correct compound? Yes. The other way to do this is to start with the other alcohol, the CH3OH. So I can either start with either R group. And don't say well, based upon the way you wrote it, you have to do this because I could turn the molecule around. Notice then I'm going to react the alcohol again with sodium metal. All that does is deprotonates the alcohol. Then I ask myself, what alkyl halide would I use here? Okay, and the one I'm going to use, the halide that I'm going to use is going to be this one. Now and again, this comes in, backside attacks, kicking the chlorine off. Now let me ask a question. One of these methods works much better than the other one. So if you were doing the test, would you use the first method on top or the second method on the bottom? Where you look is the second step, where the SN2 reaction occurs. Notice the nucleophile here is attacking a very unhindered halide. This is actually a methyl halide, and we know that methyls are better than primaries or better than secondaries. Notice in the second reaction, the nucleophile is attacking this carbon, which happens to be an sp2 hybridized carbon. And normally SN2 reactions do not attack sp2 hybridized carbons in a carbon-carbon double bond. Okay, so the bottom reaction does not work. So the first thing we're going to say is, in a Williamson ether synthesis, the first step doesn't matter. The sodium metal is going to pull off and deprotonate any alcohol. It's the second step that we have to look at, the SN2 step. Now what we're going to do is we're going to look at one more reaction that you saw, and this is on page 8. And this is the alkoxymercuration demercuration reaction. And I'll put this in a little more detail than I did in my notes. We've got this alkene, and I'm going to turn it up on its side. And if you look in your notes, whenever you developed your note cards from last semester, remember we chose to put CH3s here, CH3s here, a CH3 here, and an H here so that we could have different substitutions on the carbon. And the reagent that we chose here was mercury acetate in step 1. And then in step 2, we could either add an alcohol or we could add water. We're going to add an alcohol here. So I think actually what I did in the notes before was I put the alcohol up here, and then in step 2, we added the NaBH4OH minus. Okay, so notice here is my alcohol. What this ended up giving me was this, a C hooked to a C, the CH3, the CH3, the CH3, and the H. But what happened? We added H and OR across the double bond, anti-addition, and it went Markovnikov. So the H added here, and the OR group added here. Now, this is not a new reaction. We saw this reaction back in Chapter 8. It's just reintroduced here because notice that this, by adding the OR, you get an ether in the reaction. So you should already have that note in that reaction in your notes. Okay? So this is pretty straightforward. We can also do the intermolecular reaction where we take 2 alcohols and form the ether on page 8. That one will not be on the test, the intermolecular dehydration reaction. The only new reaction that we're going to learn this semester, or in this section rather, for ethers is on chapter 9 or on page 9 of this. So let's look at the reaction with HBr or HI. And this is really the only reaction that ethers undergo. That's why ethers are such good solvents. They don't undergo very many reactions. It's hard to destroy an ether. what you have to add is either concentrated HBr or concentrated HI to get this reaction to occur. And here's the reaction. I'm going to illustrate this with HBr, but it also works for HI. It does not work for HCl. Okay, if we take an ether and react it with HBr, and let's put 2 of them in there, what we end up getting out of this is 2 halides plus water. Now listen carefully. Don't put this reaction on your note card yet. There's some caveats. And we're going to say this a lot this semester. This is what happens in this reaction, except when it doesn't. And there's going to be a lot of excepts when it doesn't in this semester. So as you make your note cards, you need to write the except when it doesn't. What happens when it doesn't? Let's look at the reaction mechanism for this. If we take the ether and react it with H+, what do you think the H+ is going to do? It's going to protonate the oxygen. So what we get out of this is we get a protonated oxygen. Now, we also have a Br- because the H+ protonated the alcohol. The Br- then comes in and attacks one of the R groups, kicking this out. That's an SN2 reaction. Okay, notice why it was so important for you to understand SN1 and SN2. That's just backside attack. By protonating this, we formed a good leaving group. So what's the product? RBr. What's the other product? R prime OH. Okay, because then isn't that what left? And remember what the R's and R primes mean. The R prime just means it does not have to be the same R group as the other one. Then we're going to take this and protonate it again. And notice what we get. The same exact thing. And the bromine can come in, backside attack. Notice the leaving group this time is water. And notice what the product is. Okay, notice what the product of this reaction is. R prime Br. So notice what we get. 2 alkyl halides. And if we do this reaction in water, the alkyl halides are insoluble in the water and they settle out from the reaction mixture. Okay? Except when this does not work. Sometimes the reaction does not occur. So let me give you an example of one that does occur, and then I'm going to give you one that does not occur. The one that does not occur is in the notes, but I want to give you another example. CH3O, CH2, CH3. And the reaction says HBr. Now, I might write out here excess, I might not. But if I write HBr or HI, you know that you have more than enough to do the reaction. So what's step 1? What's going to happen? It's going to protonate it. Now listen carefully to the next statement. So we've protonated the oxygen. Where is the bromine going to attack first? This carbon or this carbon, and why? Remember, this step is an SN2 reaction. If it's an SN2 reaction, which one's going to be most easily backside attacked? The least hindered one. So it's going to backside attack over here, kicking this off. So we're going to get CH3Br. The other product is going to be HO, and I'll just draw it out like I would normally draw it out. CH2, CH3. Putting my lone pairs on there. Can't I reprotonate this? Then will the bromine come in and a backside attack this, kicking off the water? Notice that is a primary halide. Can primary halides undergo backside attack? And the answer is yes, they can. So the next product will be ethyl bromide, and I'll write it with the bromine on the other side. I could have turned it around if I wanted to, and water is the other product. So notice in this case, we got 2 alkyl halides from the reaction. Now let's look at the reaction that's in the notes, okay, on page 9. Let's look at one that's in the notes. Okay, so we've got, anybody want to take a shot at naming that ether? Name it by the systematic method. Name it by the common method. Do you agree if you named it by the common method, it would be methyl phenyl ether? You don't know how to name it by the systematic method yet, but it would be methoxybenzene. Okay, because a 6-member ring, when it's the main chain, we'll learn in one of the next chapters, is called benzene. But let's take this and react it with HBr. What's the product? What's going to be the first thing that occurs? Protonation. Now the bromine has a choice. Where is it going to attack? It's going to attack the least hindered carbon. So when it does that, notice again, this is just SN2 backside attack. So we're going to get CH3Br. The other product is this. Now, if we were to protonate this then, we would get that. But can the bromine come in and backside attack now? And the answer is no, because this carbon that it's backside attacking is sp2 hybridized, and we just got finished saying that doesn't occur. So this would be these would be the products of this reaction, the alcohol and the bromide. Notice in this case, we did not get 2 bromides. So this is one of the cases where it doesn't occur as we would have expected it to. Now, the last thing on page 10 is probably the most important thing we need to say. And it's not a reaction you need to know, but ethers will slowly react with air, with the oxygen in the air. So if you have a can of ether and you've let it sit for 5 years, you opened it 5 years ago and poured a little bit out, the can filled up with air, you've let it sit for 5 years. Ethers react to form 2 types of compounds, hydroperoxides and dialkyl peroxides. Both of these compounds are explosive. So if you've got old ether, it's very, very dangerous. Let's suppose you walked into a building and your job was to clean up the building. You walked in there and you saw an old can of ether. What would you do with it? Pick it up and carry it out. Just by picking it up, it becomes so shock sensitive that these compounds oftentimes explode. The guy who taught me organic chemistry tells a story about, he was an old guy and he was probably, had been in a lab a lot. And he said this was his most terrifying incident in all of his years of doing chemistry in lab. he was distilling some ether. So he had some ether in a distillation, just like what we made, and he was distilling it over. Okay. As he was distilling it over, it was right after lunch. He had drank something for lunch and he needed to go to the bathroom. So he, looks at the reaction. Everything's going just the way it's supposed to, drip, drip. And he walks out of the lab. And as he walks out of the lab, he pulls the door to and starts walking down the hall. As he pulls the door to and it slams, the ether had peroxides in it and it detonated. He had about 500 milliliters of the ether in his distillation apparatus that he was distilling from and everything. And it leveled the lab down to the floor. Okay. And he tells this story and then he adds to it. So if you're ever in the lab and your bladder tells you that you need to go to the bathroom, listen to your bladder because it could save your life. Had he been in the room and just dropped something and caused a shock, he would have been killed and everything. So he said having to go to the bathroom, probably saved his life. Okay. So again, if you ever deal with ethers, you don't want to deal with ethers that are old. Whenever we buy ethers from Rome State, we buy them one semester at a time. And whatever we don't use that semester, we put in the hood and let it evaporate. We do not save our ethers for long periods of time. So if you ever go into a lab where there are old ethers in the lab, make sure that you're very, very cautious with it.